Good evening, team. Welcome back to Advent of Code with me, Corey. Today we're going to take a quick detour, and instead of solving day 15, we're going to take a look at how I made my day 14 part 2 solution over 3,000 times faster than it was before when we finished the video yesterday. We'll use cargo flamegraph to look at a flamegraph of our code, and then we'll see how we can nudge Rust to not inline functions that we might miss during profiling. So let's dive right in. Okay, let's jump back into it. Today's going to be a little bit different in that I already did make this part faster, and we're going to reenact it today, and I'm going to pretend that I don't know the answer all the way through. But first, let's do some background. But actually though, before we do the background, I'm going to go to our tests, and I'm going to run the tests in release mode and get them started. And let's go back and now explain. Those are going to take about a minute to run, so we'll get them running while I explain the problem here quick. So this is this is day 14 of Advent of Code, part 2. But basically it's about falling sand. So it's about simulating sand falling from the ceiling here. And in part 1, we assumed there wasn't a floor, and as soon as a piece fell forever, we stopped. And then in part 2, we assume that there's a floor at the bottom, and we see how many pieces of sand it takes till we can't add sand because we reach the spout. And so we're simulating that in our code here. So the correct answer for part 2 is 26,375. That's how many pieces of sand fall before the spout gets covered, basically. So if we look back at our code here, this is still running. Awesome. Okay, so what we're doing in part 2 here is we parse our input into a maze structure. We take that maze and make it into a frame, and we count how many times we can call next on that frame, and then we return the count. And there we go. So this took a minute to run. So it is running, and it is working. It's just taking a minute. So if we look through what happens in next, this is kind of the meat of our algorithm here. A frame is kind of like a snapshot in time, and calling next on it drops one piece of sand. So we start by having a sand, and we have our rocks on the board. These are where the walls are, the ampersands in these pictures where sand gets trapped if it falls. So we have those, and we say if it's blocked, if there's a rock covering where the sand starts, we're done. Else we just take a sand that starts there and have it keep falling, and it falls as long as there's a next move for it, unless it has fallen off the edge of the board. So the highest point possible, how the coordinate system works here, which confused me at the very beginning, is with 0 zeros up in the top left corner. So as we go down, the y's actually increase. So the highest y point is actually the lowest down here because of how it works. So if you're off the bottom of the board, then we can just also say we're done. And then if once the sand falls somewhere, it then becomes a rock. So it becomes a rock, we insert it into the hash map, and we have our next frame. And that works great, and it's solving in about 1 minute here. And at the end of the video yesterday, I was just trying to look at the code and see where I thought it would be slow, and I wasn't seeing it. And now it's glaring at me because I know the answer, but I'm gonna hold it back, and we're gonna go through it step by step here. So I wasn't seeing anywhere that I thought was an obvious point of being slow, and I had a working solution, and a minute felt fine. So I stopped the video there, but of course then, after that, I had a thought, and I decided to play with it more, and it's something I mentioned on video. We're going to take a look at a flame graph for this. So we're going to use flamegraph RS, or flamegraph, from the flamegraph RS repository here. And we're going to use it with the cargo prefix, so we're going to use it as cargo flamegraph. But a flamegraph, for anyone who's not familiar, is going to look like this, and it's like a profile. It's profile information. So what it tells you is how often over the course of some program duration you're in certain functions, basically. So something that shows up more often in a stack trace is something that your program is doing more often. The flame graph basically just takes snapshots in time of what's on the stack of your program and records them, and then makes this nice diagram for us. So we're going to use this to see what is taking a while in our solution here, and then hopefully that helps us figure out a way to make it faster. So we can install it by doing cargo install flamegraph, which I've already done. So this should be nice and quick. There we go, already installed. And then from there we can do So you can use it as a standalone tool, but we're going to use it with its cargo prefixes, because then we can just use it to run a test directly. And we're going to use the unit test because we already have a test written for this. That's how we were running this. So we have a test called tests my input part 2, and that's the one that took about a minute to run. So what we can do is we can generate a flame graph with this unit test. So we can do cargo flame graph, graph, dash unit test, and then we provide the unit test name after the double colon. That threw me up a little bit last night, but this should work. So then we give it the test name, tests my input part 2 with unit test. And ooh, I forgot something. And let's see, will it tell me anything about that? Yeah, it's going to. Awesome. So the thing that I forgot, and it's going to warn me about, is profiling without debug info. So I can run this, and it's going to run it in release mode. But the problem is that it's not going to have actual like function names and debug info, but it's telling me the solution. So I just got to go to my cargo.toml. And I just know this because I did it last night. This has to be in the cargo.toml of the root if you have a workspace. So since I'm in a cargo workspace, I have to do the cargo.toml in the root, not the cargo.toml in my 14 crate here. That just tripped me up. Okay, so we're profiling in bench, and we're going to turn debug symbols to true. It's going to make our binary bigger, probably makes compilation take a little while longer, but for our profiling, we're going to kind of need it. And then the other thing that this tells me that I forgot about is because I'm running on Mac OS, it's using dtrace. I think it uses something different on Linux, but really what that means is I just need to run this with sudo. So I'm going to do sudo bang bang, which is going to rerun the last command with sudo. I need to do my sudo thing, and there we go. Okay, so now it's going to run, and we just got to wait. And this will generate a flame graph for us. Interestingly enough, this didn't go away, even though I believe we set that. So if the function name doesn't come out right in this flame graph, we might end up having to use the environment variable, cargo profile bench debug, because I'm wondering if that didn't trigger. But while this is opening, I don't think I opened Chrome earlier. Chrome is what I like opening these flame graphs in. They're going to output as SVGs. And I found Chrome browser just the easiest way to open those. Okay, so this is probably going to take a little bit longer than the 1 minute that it took to do the test when we were running it before, because profiling is going to make it slower. Like checking the stack frame and like counting what we're working on is definitely going to make the program a bit slower. Okay, there we go. So now we have flame graph, and I can drag this to Chrome, and there we go. Awesome. So this is our flame graph, and I can make it bigger, but it's not a very exciting flame graph. It just shows one stack. Everything's in one line here. And at the top, it just says the next method. I can zoom in so we can read that better. It just says next, and it says we spent like all of our time in it. We spent 99.89% of our samples in the next method. And this is an unfortunate thing that'll happen sometimes if you're profiling. And you'll just end up at like the one big method you have, and it won't really tell you what's underneath. And sometimes what's happening, not all the time, but what's happening here and what I fought with last night is that all of our methods are getting inlined. So when Rust compiles our code, it realizes, oops, didn't want to print that. It realizes that it would be faster to not call the function and just like copy paste the function body basically each time. And that's what we did. It basically inlined all of next so that everything inside next where we call a function just gets inlined and becomes one function. But luckily we can tell Rust not to do that. Inline never. Yeah, so we want to add this inline never. We're going to go to an issue with it where it wasn't respected, but I just wanted to steal the syntax here. So what we can do is we can add this inline never attribute. So let's go to things under next. So like next move, maybe next move is slow. We want to see that come up in our stack trace. And we're just going to sprinkle this. Oops. We're going to sprinkle this inline never kind of just all over the place. We probably don't want to leave these in once we like figure out what might be slow. But while we're trying to figure that out, I'm kind of just going to go crazy and throw this everywhere. Okay, and now we're going to try it again. So now hopefully the idea here is now that we are not inlining these functions, we should see them in the flame graph, and hopefully we get more information than we did last time. But now I've got a minute to kill here. So, I don't know. Maybe I'll do some fancy thing in the video and we can skip ahead a few seconds here while I wait for this flame graph to run. Okay. And ready to go, we have a new flame graph. And let's just refresh the page. Should be a new file. Wait, am I zoomed in weird? Nope. There is something over here. Okay, so we call next move a little bit and hash1 a little bit and next. Okay, so we have a few more things that were inline before, but it's still just a next. Did we miss anywhere that we want to put an inline? Oh, let's put one here. I think that's the right. It's the square brackets and then yeah, square brackets and then that. Okay. So let's try that one and let's make one more flame graph here. We're gonna go into fast forward motion again. I liked that. Okay, another flame graph this time. Okay, there we go. And now we can see that the first time I just forgot the inline on the one function that I knew was going to show up here. And we can finally see that we actually are spending 99.6% of our time in this highest point possible method. And so knowing that, we can look at it and rethink our problem. So it makes a lot of sense once we see it, right? So we're in this next loop. One of the things that we do inside of a while loop is we call self.highestPointPossible. So the first thing that we can do is probably just pull this outside of the while loop. But then let's try that first. Let's just start there. So let's make this highest, self.highestPointPossible. And then this is just if it's greater than highest. Awesome. And then let's just run this let's just run the tests. And release. And we're gonna leave the inlines in. It's probably gonna make it a bit slower, but this will be a bit better. So since I had to run the flame graph with sudo because of the dtrace stuff, it messes up my cargo cache, so I just have to clean it again before I run without sudo. But that's fine. Oh, and there we go. That took our time away. Now we're down to only 0.67 seconds. And you know what's even funnier about optimizing things like this? Pulling it just out of the while loop like that isn't even what I thought of doing last night. But looking at it again with you live, that was even easier than what I did. Pulling it out of that while loop apparently saves us all of the time we were doing. And we can even flame graph it again. Yeah, so let's have it run a flame graph while I talk about what I did instead. Oh wow, that flame graph was too fast. I didn't have time to talk. But now we spend time. We still spend quite a bit of time in highest point possible, but it's so fast that it's not even a big deal to me where we spend time. We spend a bit of time in next move. I think that's the sand moving method. And awesome. Okay. Well, I do want to say what I did because I think it's an interesting way to structure it. What I realized is I actually have two concepts that are kind of representing a similar thing, and it's kind of left over from adapting part 1 into part 2. We have highest point possible, which I started with in part 1 when there wasn't a floor, and I needed a way to say if something reaches these points, we're done and we don't need to keep simulating forever. And that's when I came up with highest point possible, and I just wrote it as a method because it just seemed like the easiest way to do it, and we were dealing with small enough numbers in part 1 that it didn't matter. And then in part 2, the floor came around, and I added the floor differently. And we think about the floor in a different spot. We think about the floor when we are a piece of sand falling down, and it knows that it can't fall if we're on a floor, or that if you hit a floor, it acts like there is a rock below it and you stack on top of it, kind of thing. And that's all fine and dandy, and those kind of worked fine together. They didn't interact, but they are kind of trying to approximate the same thing. There is some point where we either don't care if you fall down, or you can't fall because it's a wall and it's like infinite in all sides. So what I did last night was I refactored my structs up here so that instead of having floor be an option, we did something more like this, where we had floor be a U64, and then we have a boolean for like floor is solid. And we do this instead. So now the floor here just becomes the highest point, and we calculate it before we create the frame. So then we just need to do something like this max y and floor addition. We just actually are gonna do that in both cases. So we actually don't have a into frame with and without floor anymore. We're just gonna always have a floor. It's just when we don't have a floor, what we're really gonna do is do floor is solid. It's false. But we're still gonna calculate it. So like maybe what we want to do is solid a boolean, and then this passes through floor is solid is solid. There is no summing of this. So we're gonna take in this, and then this is just gonna call self dot into frame with floor where it is not solid. Not the cleanest naming, but it's going to work with what we already have. So then we're going to say that the floor is or isn't solid, depending on this boolean. Okay, so then when we go to use this, when we go up here and we want to use it, oh, so this one is false. It's not solid here. But when we go up to use it here, we're not going to check that the floor is an option. We're going to say if a frame dot floor is solid. If that, we don't need that. So we can actually just combine this with this if. So if the floor is solid and we are on it, then you can't go down anymore. And then similarly, down in the other place where we were talking about the floor before, oh, this needs a floor. This just needs to pass through. Floor is solid. Self dot floor is solid. And then here, this isn't highest. This just becomes self dot floor. If sand is greater than self.floor. Yeah, so if we ever get below the floor, not equal to the floor, but below the floor, then we can return none. But we're not going to get here if it's solid. So I guess another thing that we could do is we could do assert equals that self.floor is solid. Is, what do we want to say? The floor is not solid here. We couldn't get here if the floor was solid because the sand would have stopped on the floor. Awesome. So this is just going to be a panic message that'll help us out if for some reason we actually get into this case when we don't expect to. And now we can just clean up a few things. We don't need the distance after methods anymore. We actually don't need this method at all. We're only going to calculate it before we make the frame. And like, just because we're cleaning up, let's clean up all of our inlines. There we go. Awesome. Okay, and let's just do a cargo clean, and then do a cargo test release. This one should be even faster than it was before. Oh, it is, but it's broken. Did I break it? Oh, it's a different number for both of these parts. Okay, so that actually is not giving us the right thing. Oh, it's the same as part 1. It's doing the same thing. So it's not, the part 2 isn't working. So is it saying that it is solid and I did false? Because that would be funny. That's definitely what happened. Let's try this again. There we go. Okay. And now in release mode, it finished so fast that we just get zeros across the board. Finished so fast in release mode that, even debug mode doesn't take too long. It ended in almost under 2 seconds in debug mode. So there we go. We were able to make the day 14 part 2 over 3,000 times faster, even more than that really in this new revised version that gets zeros on our clock, infinitely faster in some sense. And I hope you learned something. I hope you learned maybe something about flamegraphs or cargo flamegraph or something, or just had fun working along with me. I had fun making this faster, and